All right, let's talk about some magnets. When I'm talking about magnets here, just a quick note that they act very similar to positive and negative charges when you put them together. So just sometimes it's nice to just use that as kind of an analogy between North Pole and South Pole being like positive charge and a negative charge. So just keep that in mind when we're drawing stuff and things like that. But anyways, the biggest similarity between magnets and, say, charges is they create a field. Okay, now I've drawn a couple different diagrams here. I've got a simple or common bar magnet, and then I've got some sort of horseshoe magnet. These are pretty common particular ones, or you can get the little like flat round disc ones that one side is north and the other side is south. One thing to keep in mind is that magnets are north and south based on the material itself. It's kind of a quality of a magnet to have a north and south pole. Now, one thing that's kind of fun to talk about is, okay, if I snap this particular bar in half, do I get a north side and a south side? And the answer is no. When you break it, this side becomes the south side, this side becomes the north side of this one. So it's as if you cannot somehow get what's called a magnetic monopole. For some reason, no matter what, that material will always have a north and a south pole. Okay, so that's kind of a fun thing to think about. Now, if I take this particular bar magnet and I hung it by a string, you'd essentially have a compass, okay, where the north end goes to the North Pole, geographical North Pole, and the south would go towards the South Pole. Now, I've drawn, and I screwed up a little bit on my drawing here, so and I'll explain why. Okay, I've got drawn in that on the Earth. Okay, well we say there's a North Pole and a South Pole. Now there's geographical north and south, but if we think about it, if a compass needle will point towards magnetic north, which I've drawn over here, and I should have drawn this particular structure. I tried to draw a bar mass as being part of the Earth here. But technically, if the compass moves towards magnetic north, it's actually being attracted to a magnetic south pole. So even though we have a geographical north pole, technically it is a south magnetic pole, which is sometimes kind of interesting to think about. But there's also this thing called magnetic declination, which is the angle between geographical north and then the magnetic north right there. Okay. So anyways, a north tip of a compass will always point towards magnetic south pole. Now I've just listed these as north poles, but keep in mind, magnetically, if we're going to call that the North Pole, it's attracting the northern part of the compass, it's technically a south pole magnet. Okay. Alright, so the next thing about magnets that we need to know, they do create a field. Magnetic fields get the symbol B, and you're just going to have to deal with it. So big capital letter B stands for magnetic field. It is measured in Teslas. And Teslas as a unit give the big capital T. You're probably going to see more commonly like milliteslas. So you might see little m and t, capital T. But just be prepared for magnetic fields as B, measured in Tesla's T. Now, I've drawn a couple pictures here. So again, if I take my bar magnet and I want to draw in the field that it creates, notice that it's really similar to charges. If this was a plus charge and this was a negative charge, we get the same exact picture. Okay, the field lines come from the North Pole towards the South Pole. That is the direction that they are drawn in. Okay, very similar to positive to negative. It's drawn from the positive because we define an electric field as the direction that a positive test charge would travel. In a magnetic field, okay, it's simply always from North Pole to South Pole. This is a bit loopy. There's lots and lots of loops in this one. Down here, if I had the North Pole and the South Pole, very similar to, say, this situation, okay, where I've got one side directly across from the other and some empty space in between, you get what's called a uniform magnetic field. So if you can manage to line up a big pole, a big north pole and a big south pole, okay, then basically the field goes directly between it. And this looks an awful lot like, say, when we have a bunch of positive charge plate and a negative charge plate, and the electric field goes between it. Okay, so there are quite a few similarities between magnets and charges so far. Okay.